Good day, everyone. This time we will talk about light waves. Discussant, yours truly, Seleni Onilongo Rodrigo. Before we define light waves, let's have a brief historical theories of light waves. Sir Isaac Newton believed that light behaves like a particle, while Christian Huygens believes that light behaves like a wave. A third scientist, Louis de Broglie, came up with what is now known as the dual nature of light. He explained that light can be a particle and can also be a wave. James Clerk Maxwell proposed the electromagnetic theory of light. Light or visible light is electromagnetic radiation within the portion of the electromagnetic spectrum that can be perceived by the human eye. Visible light consists of light waves with frequencies between 430 trillion Hz and 760 trillion Hz, while invisible light has light waves with frequencies of less than 430 trillion Hz or greater than 760 trillion Hz. We have two characteristics of light waves: brightness or intensity and color. A brightness or intensity depends on the source and the distance from the source. As light travels, it is spreading out and covering a larger area, while color is determined by the wavelength of the light wave. The narrow range of wavelengths and frequencies in the electromagnetic spectrum that humans can see is the visible light. Different wavelengths can be seen as different color. The longest wavelength is seen as red light and the shortest as violet light. Light travels in a straight line. Light waves, like all waves, travel from the source in all directions. If you could trace the path of one light wave as it travels from a light source, you would find that the path is a straight line. Because light waves travel in straight lines, the path and the direction of a light wave can be shown with an arrow called ray. Also, we have two sources of light. First is the natural source of light. It is an object capable of producing its own light. For examples, sunlight, moonlight, lightning, stars, and firefly. The second source of light is artificial. The energy transformation is needed to convert or transform forms of energy to light or other forms. For examples, lamps, bulbs, and flashlights. Next is electromagnetic wave. The visible light that we can see is just a tiny part of the electromagnetic spectrum. Visible light is made of photons with medium energy. Photons with more energy are ultraviolet radiation, X-rays, and gamma rays, while photons with less energy are infrared and radio waves. Here are the list of different types of light waves: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Let us discuss first about radio waves. Radio waves are at the red end of the electromagnetic spectrum. The red end is also the lowest energy, the lowest frequency, and the longest wavelength. Radio waves are mostly used in communications to send signals from one place to another. Radio stations, unsurprisingly, use radio waves as do cell phones, televisions, and wireless networking. Due to the long wavelength of radio waves, they can be bounced off the Earth's ionosphere, allowing radio stations to transmit their broadcasts over long distances without being in line of sight of all their listeners. But how do we see using radio waves? Objects in space, such as planets and comets, giant clouds of gas and dust, and stars and galaxies, emit light at many different wavelengths. Some of the light they emit has very large wavelengths, sometimes as long as a mile. But we can see them through radio telescope. But what is radio telescope? Radio telescope Look toward the heavens at planets and comets, giant clouds of gas and dust and stars and galaxies. By studying the radio waves originating from these sources, astronomers can learn about their composition, structure, and motion. Radio astronomy has the advantage that sunlight, clouds, and rain do not affect observation. Another type of light wave that belongs to less energy is microwave. Microwave have wavelengths that can be measured in centimeters. The longer microwaves, those closer to a foot in length, are the waves which heat our food in a microwave oven. Microwaves are good for transmitting information from one place to another because microwave energy can penetrate haze, light rain and snow, clouds, and smoke. Shorter microwaves are used in remote sensing. These microwaves are used for radar like the Doppler radar used in weather forecasts. Microwaves used for radar are just a few inches long. This microwave tower can transmit information like telephone calls and computer data from one city to another. But how do we see using microwaves? Radar is an acronym for radio detection and ranging. Radar was developed to detect objects and determine their range, or position, by transmitting short bursts of microwaves. The strength and origin of echoes received from objects that were hit by the microwaves is then recorded. Because radar senses electromagnetic waves that are a reflection of an active transmission, radar is considered as active remote sensing system. Passive remote sensing refers to the sensing of electromagnetic waves which did not originate from the satellite or sensor itself. The sensor is just a passive observer. How do microwaves show us? Because microwaves can penetrate haze, light, rain, and snow, clouds, and smoke. These waves are good for viewing the Earth from space. The ERS-1 satellite sent out wavelengths about 5.7 centimeter long. This image shows sea ice breaking off the shores of Alaska. The GERS satellite uses wavelengths about 20 centimeter in length. This is an image of Amazon River in Brazil. And lastly, this is a radar image acquired from the Space Shuttle. It is also used a wavelength in the L-band of the microwave spectrum. Here we see a computer-enhanced radar image of some mountains on the edge of Salt Lake City, Utah. Let's proceed to infrared light. Lies between the visible and microwave portions of the electromagnetic spectrum. Infrared light has a range of wavelengths, just like the visible light has wavelengths that range from red light to violet. Far infrared waves are thermal. In other words, we experience this type of infrared radiation every day in the form of heat. The heat that we feel from sunlight, a fire, a radiator, or a warm sidewalks is infrared. Shorter or near infrared waves are not hot at all. In fact, you cannot even feel them. These shorter wavelengths are the ones used by your TV's remote control. But how do we see using infrared? Since the primary source of infrared radiation is heat or thermal radiation, any object which has a temperature radiates in the infrared. The warmer the object, the more infrared radiation it emits. The human body has a temperature that produces radiation in this part of the spectrum, and so infrared detectors can be used as night vision cameras. Also, using cell phones, infrared camera, and other satellites like the Infrared Astronomy Satellite or the IRAS, look up into the space and measure the infrared light coming from things like large clouds of dust and gas, stars, and galaxies. Many things beside people and animals emit infrared light. The Earth, the Sun, and faraway things like stars and galaxies do also. For a view from Earth orbit, whether we are looking out into space or down at Earth, we can see used instruments on board satellites. Instruments on board satellites can also take pictures of things in space. The image below of the center region of our galaxy was taken by IRAS. The hazy horizontal S-shaped feature that causes the image is faint heat emitted by dust in the plane of the solar system. Visible light waves are the only electromagnetic waves we can see. We see these waves as the true colors of the rainbow. Each color has a different wavelength. Red has the longest wavelength and violet has the shortest wavelength. When all the waves are seen together, they make white light. When white light shines through a prism or through water vapor like this rainbow, the white light is broken apart into the colors of the visible light spectrum. Now, let's move on to type of light waves that belong to more energy, the ultraviolet. Ultraviolet, often shortened to UV, is heading to the blue side of the electromagnetic spectrum, which is the high energy and the shorter wavelength side. UV waves are high enough energy that they are capable of ionizing atoms, breaking molecular bonds, and even damaging DNA molecules. For this reason, it is UV that causes sunburn and therefore skin cancer. Most of the sun's harmful UV waves are absorbed by the atmosphere, especially the nitrogen, and the ozone layer, but enough gets through that we have to be careful by wearing sunscreen and using UVI protection. Our sun emits light at all the different wavelengths in electromagnetic spectrum, but it is ultraviolet waves that are responsible for causing our sunburns. To the left is an image of the sun taken at an extreme ultraviolet wavelength. This image was taken by a satellite named SOHO, and it shows what the sun looked like on April 24, 2000. Another more energy light wave is X-rays. X-rays are very high energy and like UV, they can ionize atoms in the body and cause damage. However, at the right wavelengths and in the right quantities, they can be safely bounced off body tissues to create X-ray images of the inside of the human body. X-rays are also created by neutron stars, black holes and nebulae, and X-ray telescope are therefore useful in astrophysics research. An X-ray telescope is a telescope that is designed to observe the remote objects in the X-ray spectrum. In order to get above the Earth's atmosphere, which is opaque to X-rays, X-ray telescope must be mounted on high-altitude rockets, balloons, or artificial satellite. This is the Whirlpool, the common name of M51, a spiral galaxy estimated to be 50,000 to 100,000 light years across. The purple dots that make it look like the biggest neon sign in the universe are X-ray sources as seen by NASA's Chandra X-ray Observatory. Lastly, and the most energy light wave is the gamma rays. Gamma rays have the smallest wavelengths and the most energy of any other wave in the electromagnetic spectrum. These waves are generated by radioactive atoms and in nuclear explosions. Gamma rays can kill living cells, a fact which medicine uses to its advantage, using gamma rays to kill cancerous cells. Gamma rays are the most energetic form of light and are produced by the hottest regions of the universe. They are also produced by such violent events as supernova explosions or the destructions of atoms, and by less dramatic events, such as the decay of radioactive material in space. Things like supernova explosion, neutron stars and pulsars and black holes are all sources of celestial gamma rays. If you could see gamma rays, these two spinning neutron stars or pulsars would be among the brightest objects in the sky. This computer processed image shows the Crab Nebula pulsar below and right of the center, and the Gemena pulsar above and left of center in the light of gamma rays. Again, the different types of light waves include radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, wherein radio waves have the longest wavelength, lowest energy and frequency, while gamma rays have the smallest wavelengths but the most energy of any other wave in the electromagnetic spectrum. Before I end my report, let me cite some importance about light waves. Light can be visible as sunlight. It can also be invisible like ultraviolet rays. The source of light can be natural or artificial. Light has brightness or intensity and color as its characteristics. Light travels in straight lines but is bent when it passes from one medium to another in a process called refraction. The visible light that we can see is just a tiny part of the electromagnetic spectrum. Visible light is made of photons with medium energy. Photons with more energy are ultraviolet radiation, X-rays, and gamma rays, while photons with less energy are infrared and radio waves, wherein gamma rays have the most energy and radio waves have the least energy. That's all about light waves. Thank you and I hope you learned something.